students, welcome to our YouTube channel Experience Tutor. Today we'll discuss Class 11th Physics, Laws of Motion, Chapter 5, NCERT Solution, Part 1. Our mission is to provide free classes on YouTube for all the students of Class 6 to Class 12 and also for the students who are preparing for IIT JEE and NEET, NDA and other entrance examinations. Before we begin, we request you to subscribe, like, and share our channel. Let us begin with the course. So, today we'll do the exercise, and first question is 5.1. Let us see question number A. A drop of rain. So, what we have to do here, give the magnitude and direction of the net force acting on a drop of rain falling down with a constant speed. So the answer is zero net force. Why? The drop off is falling with a constant speed. Here, this is important thing, constant speed. Hence, the exertion is zero. We know that for constant speed, exertion is zero. As per Newton's second law of motion, F is equal to ma. The net force acting on the raindrop is zero because the exertion is zero. Now let us see the question number B. A cork of mass 10 gram floating on water. Answer is zero net force. Why? Because the weight of the cork is acting downward. It is balanced by the buoyant force exerted by the water in the upward direction. So this is the buoyant force which is acting upward, and this is the weight which is acting downward. These two balance each other. Hence, no net force is acting on the floating cork. Now, question number C. A kite, a kite skillfully held stationary in the sky. Answer is zero net force. Why? Because the kite is stationary in sky, so stationary means it is not moving at all. As per the Newton's first law of motion, no net force is acting on the kite. Now, question number D. A car moving with a constant velocity of 30 km per hour on a rough road. Zero net force. The car moving on a rough road with a constant velocity, this is the important point, constant velocity. Hence, the acceleration is zero. So, since the constant velocity, acceleration is zero, as per Newton's second law of motion, no net force is acting on the car. Now, we'll do question number E. A high-speed electron in space, far from all material object and free from electric and magnetic fields. Zero net force. The high-speed electron is free from the influence of all fields. Hence, no net force is acting on the electron. Now, let us see 5.2. A pebble of mass 0.05 kg is thrown vertically upward. Give the direction and magnitude of the net force on the pebble. A during upward motion. So first let us see the solution for A. Okay, then let us go through all the questions, then we'll see the solution at one. So at one time. So A is during the upward motion, B is during the downward motion, C is at a large point where it is momentarily at rest. Do your answers change if the pebble was thrown at an angle 45 degrees with the horizontal direction? Ignore air resistance. So let us see the solution part. Zero point 0.5 Newton is vertically downward direction in all the cases, A, B, C, all the cases. Acceleration due to gravity, irrespective to all the direction of motion of an object, always acts downward. The gravitational force is the only force that acts on the pebble in all these cases. Its magnitude is given by Newton per second's law of motion. F is equal to ma, where F is equal to net force, m is equal to mass of the pebble, and a is equal to g, which is 10 meter per second square. After calculating, we get F is equal to zero point 0.05 into 10, which is 0.5 n. So initially we have written the answer as 0.5 n. So this is how we got the answer 0.5 m. Now we have calculated the force. Now let us see the rest of the questions. The net force on the pebble in all the three cases is 0.5 Newton, and this force acts downward direction. So direction is also given. If the pebble, now the last part, if the pebble is thrown at an angle 45 degree with the horizontal, it will have both the horizontal and vertical components of velocity. At the highest point, only the vertical component of velocity will become zero. So let us understand here. So this is the horizontal. Now this is thrown 45-degree angle. So the object will move in this way. So at highest point here, what will happen? Uh, Here, so first let us draw the components. So for this 45-degree, this is 45-degree. So we have to, there will be two components here. One is vertical, one is horizontal. This will be V cos theta, that is 45-degree, and this will be V sin theta, that is sin 45-degree. Now at this point, at maximum height, when it will stop moving upward, what will happen? The vertical component, this one. So which is the vertical component? V sin theta, V sin 45-degree will be equal to 0, because it is moving, stop moving. The vertical component will become 0 because it is stop moving upward. Now from this point it will come downward. However, the pebble will have horizontal component of velocity throughout the motion, but this component v cos 45-degree will be available throughout the motion, and this component of velocity produce no effect on the net force acting on the pebble. So it will have no effect on the net force acting on the pebble. So this is the complete answer of 5.2. Now let us check the next question, that is 5.3. Ignore air resistance. Okay. Give the magnitude and direction of net force acting on the stone of mass 0.1 kg. A. Just after it is dropped from the window of a stationary train. B. Just after it is dropped from a window of a train running at a constant velocity of 36 km per hour. C. Just after it is dropped from a window of a train accelerating with 1 meter per second square. D. Lying on the floor of a train which is accelerating with 1 meter per second square, the stone being at rest relative to the train. So let us see the first part of the question, question A. Answer is 1 Newton. Vertically, direction is vertically downward. So we have to explain why, how this came. Now, mass of the stone is given, m is equal to 1.1 kg. Acceleration of the stone is given, a is equal to g is equal to 10 meter per second square. As per Newton's second law of motion, the net force acting on the stone, F is equal to ma is equal to mg, which is 0.1 into 10, that is 1 Newton. Acceleration due to gravity always acts in the downward direction. So 1 Newton and vertically downward is clear. With a simple formula, F is equal to ma, which is equal to mg here. Put the values of m and g and we can get it. Now the second, now the B part. Answer is again 1 Newton. Direction is vertically downward. How? Let us see. The train is moving with a constant velocity. It is given. Hence, its acceleration is 0. We know that for constant velocity, acceleration is always 0. In the direction of its motion, that is in the horizontal direction. The net force acting on the stone is because of acceleration due to gravity, and it always acts vertically downward. The magnitude of the force is 1 Newton. Now let us see the part C. Answer is 1 Newton vertically downward. Direction is vertically downward. Let us see how it comes. It is given that the train is accelerating at a rate of 1 meter per second square. Therefore, the net force acting on the stone, F is equal to ma, that is zero point 0.1 into 1, that is zero point 0.1 Newton. This force is acting in the horizontal direction. Now, when the stone is dropped, the horizontal force F dash stops acting on the stone. This is because of the fact that the force acting on the body at an instant depends on the situation at that instant and not on the earlier situation. Therefore, the net force acting on the stone is given by the acceleration due to gravity. And the acceleration due to gravity is equal to F is equal to mg, that is 1 Newton. Part D. 0.1 Newton is the answer, and the direction of motion of the train. Direction is in the direction of the motion of the train. The weight of the stone is balanced by the normal reaction of the floor. The only acceleration is provided by the horizontal motion of the train. Acceleration of the train is a is equal to 0.1 meter per second square. The net force acting on the stone will be in the direction of the motion of the train. Its magnitude is given by F is equal to ma, that is zero point 0.1 into 1, that is zero point 0.1 Newton. So this is the end of the question. Let us see the next question. Let us see question number 5.4. One end of a string length L is connected to the particular to a particle of mass m, and the other end to a small peg on on a smooth horizontal table. If the particle moves in a circle with speed v, the net force on the particle direction its towards the center is a t 2 t minus mv square upon L third t plus mv square upon L fourth 0. T is the tension of the string. Choose the correct alternative. Answer is uh, 1, that is T. Now, when a particle connected to a string revolves in a circular path around the center, the centripetal force provided by the tension produced in the screen. Hence, in the given case, the net force on the particle is the positive T. That is, F is equal to T is equal to mv square upon T. When mv square upon T, where F is the net force acting on the particle. So remember this. So let us see the next question. So question number 5.5. A constant retarding force of 50 Newton is applied to a body of mass 20 kg moving initially with a speed of 15 meter per second. How long does the body take to stop? So let us see the solution. Retarding force F is equal to minus 50 Newton. So since the force is retarding force, so minus sign. Mass of the body is 20 kg. This is also given. Initial velocity of the body is u is equal to 15 meter per second. Final velocity of the body v is equal to 0, because the object finally stops due to the retarding force. Using Newton's second law of motion, the exertion A produced by the body can be calculated as F is equal to ma, that is, put the value of F is equal to minus 50, m is equal to 20. We can find out the value of A as minus 50 upon 20. So after cancelling, we get minus 2.5 meter per second square. Now, using the first equation of motion, the time t taken by the body to comes to rest can be calculated. V is equal to u plus at. Therefore, t is equal to minus u by a, which is equal to minus 15 by minus 2.5, that is 6 seconds. Now, let us see the next question, which is 5.6. So 5.6 question is, a constant force acting on a body of mass 3 kg changes its speed from 2 meter per second to 3.5 meter per second in 25 seconds. The direction of the force of the body remains unchanged. What is the magnitude and direction of the force? The solution is mass of the body is equal to 3 kg. So initial speed of the body is also given, that is 2 meter per second. The final speed of the body is equal to v is equal to 3.5 meter per second. Time is equal to t is equal to 25 seconds. Using the first law of motion, the acceleration A produced in the body can be calculated as v is equal to u plus at. So A is equal to v minus u upon t. Put the value of v and u. So 3.5 minus 2 upon 25, which is equal to 1.5 upon 225, which is equal to 0.06 meter per second square. Now, as per Newton's second law of motion, force is given by F is equal to ma. So putting the value of m and a, we got 3 into zero point 0.06, which is equal to 0.18. Such, since the application of force does not change the direction of the body, the net force acting on the body is in the direction of the motion, of its motion. So now we'll carry out with 5.7. A body of mass 5 kg is acted upon by two per perpendicular forces 8 Newton and 6 Newton. Give the magnitude and direction of the acceleration of the body. 5.7 solution. So 2 meter per second square is the acceleration, is the answer for acceleration. And direction is at the angle of 37 degree with the force of 8 Newton. So this is the answer. But now we'll give the explanation. So mass of the body m is equal to 0.5 kg. The given situation can be represented as follows. The resultant of two forces is as is given as r is equal to, so first see the figure here. So this is the resultant which we are talking, and this is the one force, this is one force, and this is the other force. So resultant is equal to r is equal to under root 8 square plus minus 6 whole square. So which is equal to 64 up plus 36, which is root 10, that is root 100, that is 10 Newton. So theta is the angle made by r with force of 8 Newton. Therefore theta is equal to 10 inverse minus 6 by 8 is equal to minus 3687. The negative sign indicates that theta is in the clockwise direction with respect to the force of magnitude, that is 8 Newton. As per Newton's second law of motion, the acceleration of the body is given as F is equal to ma, A is equal to F by m, that is 10 by 5 is equal to 2 meter per second square. 2 meter per second square is the answer. Now we'll do question 5.8. The driver of a three-wheeler moving with a speed 36 km per hour. The driver of a three-wheeler moving with a speed of 36 km per hour sees a child standing on the middle of the road and brings his vehicle to rest. in 4 seconds. Just so just 4 seconds just in the time of in the time to save the child. What is the average retarding force of the vehicle? The mass of the three-wheeler is 400 kilo or kg, and the mass of the driver is 65 kg. So you have to find out the retarding force. Initial speed of the three-wheeler is 36 km per hour. The speed of the three-wheeler in meter per second is 10 meter per second. Time is equal to 4 seconds. So mass of the three-wheeler is 400. Mass of the three-wheeler driver is 65 kg. The total mass of the system m is equal to 400 plus 65, that is 465 kg. So using the first law of motion, the acceleration a of the three-wheeler can be calculated as v is equal to u plus at, and a is equal to v minus u upon t, that is 0 minus 10 upon 4. Final velocity is 0. So upon calculating, we get acceleration is equal to minus 2.5 meter per second square. The negative sign indicates that the velocity of the three-wheeler is decreasing with time. Now, using the Newton's second law of motion, the net force acting on the three-wheeler can be calculated as F is equal to ma. Put the value of mass and acceleration, we get 1162.5 Newton. The negative sign indicates that the velocity of the three-wheeler is decreasing with time. Now, using the Newton's second law of motion, the net force acting on the three-wheeler can be calculated as F is equal to ma. Put the value of F as 465, m as put the value of m as 465 and a as 0.25 minus 0.25, and therefore the retarding force is equal to 1662.5. The negative sign indicates that force is acting against the direction of the motion of the three-wheeler. Now let us move question number 5.9. A rocket with the lift of mass 20,000 kg is blasted upward with a initial acceleration of 5 meter per second square. Calculate the initial thrust, that is force of the blast. So mass of the rocket is equal to m is equal to 20,000 kg. Initial acceleration a is equal to 5 meter per second square. Now acceleration due to gravity g is equal to 10 meter per second square. Using Newton's second law of motion, the net force or thrust acting on the rocket is given by the relation F minus mg is equal to ma. F is equal to m bracket g plus a. Now F minus mg is equal to ma. F is equal to m common g plus a. Put the value of m as 20,000, g as 10, and a as 5. we get 20,000 into 15, that is 3 into 10 to the 5 Newton. This is the answer. Now let us move to the 10th question, that is 5.10. A body of mass 40 kg moving initially with a constant speed of 10 meter per second to the north is subject to a constant force of 8 Newton directed towards the south of 30 seconds. Take the instant force instant the force. Take the instant the force is applied to be t is equal to 0. The position of the body at that time to be x is equal to 0 and predict its position at t is equal to 5 seconds, 25 seconds and 100 seconds. So mass of the body is given by m is equal to zero point 0.4 kg. Instant speed of the body u is equal to 10 meter per second due to north. Force acting on the body F is equal to minus 8 Newton. Acceleration due to acceleration produced in the body is equal to A is equal to F by M, that is minus 8 upon zero point 0.4, that is minus 20 per second square. At t is equal to 5 seconds, at t is equal to 5 seconds, acceleration A dash is equal to 0 and u is equal to A dash is equal to 0 and u is equal to 10 meter per second. S is equal to ut plus half a dash t square. So we can write 10 into minus 5, that is minus 50. So uh, at t is equal to 25 second, acceleration is equal to a double dash is equal to minus 20 meter per second, u is equal to 10 meter per second. So equation of motion s is equal to ut plus half a double dash t square. Put the values, we get minus 6,000 meter, minus 6,000 meter. So distance is equal to minus 6,000 meter. T is equal to 100 seconds. For t greater than 0 and smaller than 30 seconds, a is equal to minus 20 meter per second square. U is equal to 10 meter per second. S is equal to ut plus half a double dash t square. Put the values, we get minus 8,700 meter. So for a for t is greater than 30 and less than 100 seconds, as per the first equation of motion, t is equal to 30 seconds. Final velocity is given to b is equal to u plus at. Put the values, we get minus 590 meter per second. For motion between the 30 second to 100 second, that is of 70 second, s2 is equal to u2 plus half it is square a dash t square is equal to half a double dash t square. So put the values, we get minus 41,300 meter. Therefore, the total distance s double dash is equal to s1 plus s2, that is minus 8,700 minus 41,300, that is minus 50,000 meter, and this is the answer. And this is the end of today's class. Before we close, we again request you to subscribe, like and share our YouTube channel. Please click on the subscribe button to support us and also click on the bell icon to get automatic notification whenever a new video is uploaded. Thank you very much for your support and watching our videos.